Good morning and welcome everyone to the pre-recorded lecture of this week, dated 11th September 2020. And we will continue to discuss about the equipotential surfaces and international reference ellipsoids, the stuff that we have been discussing so far. So, what we have gathered so far that international reference ellipsoid provides us closest approximation of this shape of the earth. Not only that, so international reference ellipsoid also provides us the closest approximation of the equipotential surface. Okay. And let us say at this equipotential surface, wherever we measure small t, okay, or I mean, to go with our earlier convention, wherever we measure small ag, we can also call it g, the gravitational acceleration. We can call it as the theoretical gravitational acceleration. Okay? And let us denote it with Gn. Okay? So what I mean that anywhere if I calculate, I can actually I can calculate the amount of acceleration due to gravity on this equipotential surface. Let us say this is the theoretical gravitational acceleration. Yeah. And let us call it as En. Now this is completely a calculated value, right? Why it is calculated value? Simply because I mean I can imagine this ellipsoid, and then I can think of a mass of this ellipsoid, and then I can think of a major axis, minor axis, and I can simply calculate at different points on this ellipsoid the value of Gn. Okay? And let us say that is the theoretical value. Okay? Now, at any point, on the Earth, one can measure small g as well. Okay? And let us say that we call as g measured or simply Em. Okay? So, two things we will be dealing with. One is Tn, that is the uh, theoretical value of the G calculated on the international reference ellipsoid. and then I will have Gm, that is the measured G at any point on the surface of the Earth. And these will be two important things that we will deal with while we use gravitational technique for our purpose. Okay. Now, I wish to bring in another important concept today, which we call as geoid. And let us see what a geoid is. Okay. Now, this is my international reference ellipsoid. And suppose I am looking at this part more closely. So I'm zooming in to this part. So let us say this is my international reference ellipsoid. And then if we actually look at the topography, if we actually look at the where there is a mountain, where there is an ocean, maybe the topography actually looks here something like this. Okay? So this is the topography, or so this is my theoretical shape of the Earth. So IRS represents the theoretical shape of the Earth, and this is the real shape of the Earth, right? Real shape. Now, so IRS, we also said this is the equipotential surface. This is the theoretical equipotential surface. So IRS is also, sorry, let me use the blue color. IRS is also the theoretical equipotential surface, right? Okay. But due to the difference in topography, the actual equipotential surface will be somewhat different than the IRS. Okay. So this is the actual equipotential surface. And this actual equipotential surface is attributed due to the change in topography. Okay. So maybe here it is positively elevated, H plus, and here it is negatively depressed, H minus. Okay. And here you can see maybe at this point the value of the actual equipotential surface and the IRS is the same. So this actual equipotential surface is called geoid. Okay. So this actual equipotential surface called geoid. Right. Now there is another important concept that I want to bring, what we call as geoid undulation. And what do I mean by geoid undulation? So what I can do at every point on the earth, at every point on the earth, I can actually calculate this H value, be it positive, be it negative. Okay? I can calculate the value of H. Okay? So let us say this is my world map. This is my world, okay? And I mean, just the map view. Okay? So here are my continents, okay? Don't worry about the shapes and everything. I mean, this is my all my continents, okay? And each point as close as possible. This depends on my how good measurements I have done. At each point, I can measure the value of H. Okay? In some places, H will be positive. In some places, H will be negative. Okay? Some places, H will be positive. In places, H will be negative. And then they will, of course, have a value. Maybe here it is 50, here it is 40, it is 30. Somewhere it will be 0 as well. And then here it is, suppose, minus 20, minus 30, so on and so forth. So I can have a, on every point on the earth, I can have a value of the H, which is, so H is the deflection, the difference between geoid and IRA, International Reference. Okay. And then what I can do, I can simply contour these values, right? You know about contouring, I talked about it before. I can simply contour these values. Yeah, I can contour H, be it positive, be it negative. So the difference between the geoid and the IRE is called geoid undulation. Okay? The difference between the geoid and the international reference ellipsoid is called geoid undulation, and then we can create a geoid undulation contour map by contouring the values of H at different parts of the world. We want to see, so as I have been explaining, so this is my reference ellipsoid, this is my geoid, and this geoid is because of the presence of a hill here. Okay, why? Because of the hill, this will be pushed up. That I will explain later on, or I can just say it right now, because of the presence of the hill, there is more mass. Okay, hence, uh, because in the calculation of G, there is a direct relationship. It's dependent on the mass. So hence my uh, geoid is pushed up from the international reference ellipsoid. Similarly, there is in the ocean there is a deficit of mass. There is a deficit of mass. You can see at this. Maybe if the ocean would have been a bit more deeper, then I would have seen the you know H going negative. But in this particular case, you can see it's very close to international reference ellipsoid. It can also go negative. That is there. Okay, and why? What is the other reason for which such positive undulation can take place? Is because of an excess mass. Okay, uh, what you are observing here, that this is my reference ellipsoid and my geoid is pushed up, and there is no, apparently there is no hill here, right? There is no hill. So the topography is flat, but still the geoid is pushed up than the international reference ellipsoid because of the presence of an excess mass in the subsurface, because of the presence of an excess mass beneath. Excess mass means that the density of this mass means, in a moment, in, yeah, yeah. So if we say that the density of this mass is rho 1 and the density of this mass is rho 2, then rho 1 is larger than rho 2. Okay. So this provides an additional effect of mass that pushes the in equipotential surface up, right? So this is positive H. This can be happening due to the presence of a hill. You can see this without the hill even, you know, this could happen because of the presence of a mass which has a higher density than the surrounding. Now, the interesting thing will be, suppose I have a hill, this is my topography, and here is my IRE, and here also beneath this I have a high density mass, okay, rho 1, rho 2, rho 1 is greater than rho 2. Okay. Now the geoid, so this is my IRE, this is the topography. So my IRE, my geoid will of course be pushed up, right? Geoid. Now it will be interesting. It will be interesting to decouple the effect from the excess mass. And this is a fairly important step that we will understand, that when we see that the geoid is pushed up, okay, because of the presence of both topography and mass, okay, or pushed down because of the presence of a negative topography and deficit of mass, how to actually decouple the effect. So we have to understand how much geoid has been pushed due to the topography, okay, and how much geoid has been pushed due to the excess mass, okay. Then if we can actually subtract the effect of topography from the total geoid undulation, we should be able to understand the effect of the excess mass. Because as you know, one of the major reasons for which we do study geophysics is to actually explode such excess masses from beneath. Okay. All right. So let's go on with the lecture. And this is a map. What you can see here is of geoid undulation. Okay. You can see here in places the contour value is positive, and then this is slowly decreasing. This is where it is zero. Zero means that this geoid and the reference ellipsoid is at the same height. Okay, and then you can see there are negative values as well. So that means at those places the geoid is pushed below the international reference ellipsoid. Okay. All right. Now let's discuss how do we actually measure small g? How do we measure small g? Okay. And that is done by an instrument called gravimeter. And there, if you will find in Lowry's book, there are multiple types of gravimeters which are described. Some gravimeters are a bit old school stuff. Some gravimeters after the incorporation of digital technology has been extremely highly precise. Okay. You can read about them, the different principles behind them. But what today I will do, I will describe you only the principle of a gravimeter, and then you can actually build up upon it in your while you read Lowry's book. Okay, I will not get into the mundane details of each gravimeter because that you can very well pick up uh, from the book itself. Okay, I'll just simply tell you about the principle of a very traditional gravimeter. Let me just first draw the picture and then I'll explain it to you. So, so this is the basic principle of a gravimeter. So you can see that there is a mass, this mass m, okay, which is actually tied with two end, one with like a very flexible arm, and then another with a spring. Okay, and then at a particular place it is calibrated so that this arm is straight and this arm is horizontal. So now at this stable position the weight of this small mass is mg. And then there is a small mirror attached to the arm. Okay, and you can see to the mirror. Okay, so the incident ray goes and then comes back on the same path. So you don't see any deflection on the light that is going down and reflected back. Okay, so you are actually observing the reflected light. In this particular case, you will not see any sort of tilt on the reflected light itself. Okay, now suppose, so this was, so is my world, okay, somewhere. Okay, so this is my position one, or let's just say this is position one is my P1, let us say, and then I have P2. So first I have taken it to P1, yeah, and then I have equilibrated it, okay, and let us say P1 is my base station. Okay? P1 is my base station, and then I have calibrated it here. Now I bring the instrument to P2. So here was my gravimeter, and here I have calibrated it. I mean, everything is kept, this rod is kept horizontal, and the incident and the reflected light is vertical. And then I bring it to P2, and let us say here my acceleration due to gravity was g, but at P2 the acceleration due to gravity is suppose g1. Okay, is changed a little bit. So what does that mean? That suppose g1 is greater than g, for example. Yeah. So what will happen to this mass? This mass will go down slightly. How much it will go down? It depends on the sensitivity of the gravimeter. Okay. So what will happen? This thing will be deflected a little bit. Now this is still m, but this force is mg1, right? And you see that this mirror is actually tilted. So if this is theta, this is tilted a little bit. So now the incident ray comes like this, but then the incident ray is deflected, and this will again be the angle theta. Okay? So you can measure this angle theta. Okay? So, but with respect to your instrument, it is a calibrated instrument. So you know that you already have, I mean, you have a pre-prepared graph where you have plotted theta against delta g. Delta g means g1 minus g, or delta g means g at a target minus g at the base station. So g at a target minus g at the base station. So you know that whatever the value of g is, maybe in milligal. So 10 degrees theta, corresponds to some milligal of, of delta G. Okay. So I measure theta. Okay. And then I can calculate that my delta G. Okay. So what scale of delta G I would be able to measure depends on the sensitivity of the gravimeter. In older days, it was used to be in the scale of millical, but with the digital technology, we have reached all the way up to microgal. Okay, we have reached all the way up to microgal. All right. So this is how we have calculated G measured. Now this G measured, or simply we can call it as GM, okay, goes through certain corrections, and those corrections are, we will see them from the next class, like latitude correction. We will explain what are these things, why the corrections are done. Booger plate correction, then elevation correction, free air correction, yeah, and so on and so forth. There are few more corrections we will discuss, tidal corrections and so on and so forth. Okay. So we measure a value at a particular point. Okay. So we measure a value at a particular point. We take it through certain corrections, and then what we get is something maybe we can call it GMC, that is the G measured. Then okay, and then we do something we call as, and then what we do, we get GMC is measured and corrected, and then we subtract it. So from GMC, GN or G normal, or the theoretical anomaly, sorry, the theoretical value is subtracted. Okay, and we can also call this one as delta G, and this delta G. So this is the measured plus corrected minus the G normal or the G theoretical. That is the small g present, small g at the international reference ellipsoid. This is what we call delta G. This delta G is also called gravity anomaly. So the sole purpose of the gravitational technique is to measure and analyze gravity anomaly. Okay? Measure, analyze, and of course, interpret gravity anomaly. And what is gravity anomaly? Gravity anomaly is the difference between G measured minus G theoretical. G measured is at a particular point, I take my gravimeter, I do a uh, g measurement, small g measurement. Okay, and then I take it through certain. Then I take it through certain corrections, and then of course I subtract it, and g small gn is subtracted from GMC. That is my gravity anomaly. All right, so I stop the class here. I'll upload it as soon as possible, and I'll see you next week. Thank you.